Okay, in the last lectures we have been talking about Bernoulli's equation and the use of Bernoulli's equation um, in, in measuring velocity using pitot static tube. For example, this is the last video on Bernoulli's equation and the last video before the mid semester. Okay, so let us consider a scenario in which we have a flow through a nozzle. Okay, we have, and let's assume that the flow is entering with uniform velocity of u1, for example. But if we take another section, for example, at the exit, okay, let us say in the exit, okay, the velocity will be 0 on the solid walls due to no slip, okay, which we have discussed earlier. So no slip will give you 0 velocity at both walls, and the velocity will have some distribution. Okay, it is not uniform, but it will have, let's say this is u2, this is a function of y. If we take this is x, y, u2 is not uniform across the cross section, and it will have a spatial distribution. So let us say this is section 1 and this is section 2. Now we want to apply Bernoulli's equation between 1 and 2. Okay, so maybe we might have measured the velocity distribution and we want to compute the pressure loss from Bernoulli's equation. Okay, so what we would do is we would assume, and let's say the same one. Okay, I assume that both geometries are exactly the same. There is no change in u1. Okay, and to apply Bernoulli's equation, we will assume uniform velocity distribution. Okay, we assume that velocity distribution is uniform, which is, let's say, u2 bar. Okay, fine. So we compute u2 bar, which is the equivalent uniform velocity profile given here from the spatial distribution of velocity. We compute u2 bar from u2 of y, okay, using mass conservation. Okay, that you can know. So integral rho u2 dA becomes rho u2 bar a2. Okay, so we compute u2 bar. Okay, this is the so u2 is a function of y, u2 bar is equivalent uniform velocity by matching the mass, by matching by enforcing the condition that mass flow rate between profile 1 and profile 2 should be the same. Okay, however this does not mean kinetic energy of these two are the same. Okay, this does not mean kinetic. So we compute equivalent uniform velocity profile from the non-uniform actual velocity field by matching the mass flow rate. That doesn't mean kinetic energies are the same. Okay, so that is where this something called kinetic energy correction factor comes into play. Okay, let us denote that as alpha. Okay, so kinetic energy correction factor alpha implies kinetic energy of the actual flow divided by the kinetic energy of the equivalent uniform profile, uniform velocity profile. Okay, so the kinetic energy of the actual flow is given by rho u2 dA. Okay, this is mass flow rate, m dot times u2 square by 2, half u2 square. Okay, that is the kinetic energy of the actual flow divided by half rho u2 bar cube times A2 is the kinetic energy of the uniform velocity profile. Okay, so this since u2 is a constant, the mass flow rate here can be written as rho u2 A2 multiplied by half u2 bar square will give us this one. Okay, so assuming in constant density, okay, alpha can be written as 1 over a integral u2 by u2 bar whole cube dA. Okay, so from this one, from here to here, this is very straightforward. Okay, so now if you are applying Bernoulli's equation for this particular example, okay, so neglecting change in potential energy, okay, so P1 plus half rho u1 square. Okay, this is at section 1 and u1 is a constant. Okay, this is uniform, u1 is uniform, so there will be no change here, is equal to P2 plus half rho u2 bar square. Okay, now this term is kinetic energy at section 2. This is not correct because now we have substituted equivalent uniform velocity distribution to account for the change in kinetic energy between the actual flow and the uniform flow. We multiply this by alpha. Okay, so when we approximate a non-uniform velocity profile into equivalent uniform one, okay, mass flow rate is the same. Okay, but kinetic energy is not the same between these two, is not, I would say, equal between these two, so corresponding correction factor should be introduced in the Bernoulli's equation. Okay, which is what we have done here, we multiplied the kinetic energy of the uniform, the equivalent uniform profile by alpha, which takes into account of this correction. Okay, in the tutorial we will solve one problem to quantify the effect of or the error we will get by not introducing alpha. Okay.